Let's now see how dynamic programming algorithm solves the edit distance problem. We start by considering two strings, A of length n and B of length m, and we will ask question what is an optimal alignment of an I prefix of A, which is the first I symbol of A, and the J prefix of B, which are the first J symbols of B. The last column of an optimal alignment is either an insertion, or a deletion, or a mismatch, or a match. And please notice that if we remove the last column from the optimal alignment of the strings, what is left is an optimal alignment of the corresponding two prefixes. And we can adjust the score of the optimal alignment for I prefix and J prefix by adding +1 in the case of insertion, +1 in the case of deletion, +1 in the case of mismatch, and adding nothing in the case of match. Let's denote dij to be the edit distance between an I prefix and a J prefix, and in this case this figure at the top of the slide illustrates the following recurrency. Dij equal to the minimum of the following four values: dij minus 1 plus 1, di minus 1j plus 1, di minus 1j minus 1 plus 1 in the case the last two symbols in the I prefix of A and the J prefix of B are different, and di minus 1 j minus 1 if the last symbol in I and J prefix are the same. Our goal now is to compute the edit distance dij between all I prefixes of string A and all J prefixes of string B. In the case of string editing and distance, we will construct 8 by 9 grid, and our goal is to compute all edit distances dij corresponding to all nodes in this grid. For example, for I and J equal to 4 and 4, how will we compute the corresponding distance dij? Let's start by filling distances di zeros in the first column of this matrix. It is easy, because indeed we are comparing an I prefix of string A against of 0 prefix of string B, and therefore these edit distances for I prefix will be equal to I. That's what's shown here. Similarly, we can easily fill the first row in this matrix. And now let's try to compute what will be the distance d11 corresponding to comparison of string consisting of a single symbol E with a string consisting of a single symbol D. There are three possible ways to arrive to the node 1, 1 from the nodes 0, 0, 0, 1, and 1, 0. Which one should be the way we will select to find the optimal edit distance? According to the previous recurrency, we should select the one of three directions that gives minimum value for dij, which is minimum of 2, 2, and 1, and therefore we arrive to node 1, 1 by diagonal edge. Let's keep this in memory that the right direction to arrive to the node 1, 1 was the diagonal direction. We will now try to compute the edit distance for the next node in the matrix, and in this case d21 is equal to minimum of d20 plus 1, d11 plus 1, and d10, which tells us that the optimal way to arrive to this node would be again by diagonal edge. We'll continue further, once again compare three values, and it turns out that the best way to arrive to this node will be by vertical edge. We'll continue further and we'll fill the whole second column in the matrix. Now let's continue with the third column. what about this node? For this node, D12 is equal to minimum of D11 plus 1, D02 plus 1, and D01 plus 1. And it is minimum of 2, 3, and 2. In fact, there are two optimal ways to arrive to this node, and in this case we show both of them by diagonal edge into this vertex and by horizontal edge in this vertex. We'll continue further, and slowly but surely we will fill the whole matrix. The edit distance pseudocode implements the algorithm we just discussed. It first fills in the first column and the first row of the dynamic programming matrix, and then it continues filling it up by computing the cost of moving to vertex ij using insertion, deletion, or mismatch, or match. Or in other words, exploring all possibility, moving to the vertex ij using vertical edge, horizontal edge, and diagonal edge. And then it finds out which of these possibilities results in the minimum edit distance.